All right, section 4, moving right along. So we're looking at factoring in this section, which is like distributing, only not. Um, he at one point talked about distributing, or I talked about distributing as like the Oprah effect. You get 2x and you get 2x and you get. We're looking at taxes now. We're taking out of everything. So it's like distributing, but in reverse. What we're looking at is what can I divide? What can I divide out of each of these terms? So we're looking for the greatest common factor. If we look at the coefficients here, we've got 5 and 15. We're asking what's the greatest common factor between 5 and 15? What can I divide both 5 and 15 by? I can divide them both by 5. Now there's no x, there's no variable in the second term here. It's just 15 or x to the 0, I guess. And so they don't have a common factor of x, but they do have a greatest common factor of 5. So this would look like this when it's been factored. So we're factoring out that greatest common factor, and you should be able to do it in reverse then and distribute and get the same thing back again. If I distribute the 5 through, 5 times x squared becomes 5x squared, 5 times 3 becomes 15. And so it does work in reverse. If we look at the second example here, I'm looking at what can I divide out of each of these terms. Well, if we just look at the coefficient, the greatest common factor between 4, 2, and 8 is 2. I can divide them all by 2. So I can divide each of those terms by 2. And if we look at the variables, they do all have a variable of x, but they have different numbers of variables. This first term has 3 x's, x times x times x. Second term has 2 x's, x times x. And the third term has just the 1x. So the greatest common factor between those 3 is 1x. And why it's not 3 is this. If you're trying to pull an x out of each of these, if you're trying to divide an x out of each of these, I can take 1x from here, because there's 1 right there. I can take 1x from here, because there's 2 of them. I can take 1x from here, because there's 3 x's. So I can take 1x from each of those terms. However, I can't take 3 x's from each of them. I can take 3 x's from this term. I can take 3 x's out of here. But there aren't 3 x's to pull from this second term. There's only 2. So I could not take 3 x's. So if x to the third, x times x times x, 3 x's, is not a common factor between the 3 of them because they don't all have 3 x's. They all have at least 1 though. So in general, when we're looking at the variables, we're asking what's the lowest exponent that they all have. They all have an x. The lowest exponent is 1. So the greatest common factor is 1x, or x to the first power. Factored out, then it would look like this. We have 2x times 2x squared becomes 4x to the third. Remember, when we multiply powers, we can add the exponents together. 2x times x is 2x squared, and 2x times 4 becomes 8x. So that's factoring out the greatest common factor, and that's a start. That's one thing we want to look for right away is there a greatest common factor we can just factor out first, and then go from there. Factoring polynomials then is kind of like FOIL, but again, backwards. So we're distributing again, it just in reverse. If we look at that first example, x plus 3 and x plus 4, if you distribute that out, you can certainly pause it and do that on your own first. But if we distribute the x through, we distribute the 3 through, and we combine our like terms, if we do that FOIL, we would end up with this, x squared plus 7x plus 12. What's important to note here, when we're looking at going back and forth between these, so in section 3, we were taking 2 binomials and we were expanding it out, or multiplying them together, I guess, into a trinomial with three terms. Now we're looking at, if we have 3 terms, can we factor it into 2 binomials being multiplied together? Looking at the numbers, looking for a pattern. If the first coefficient here is 1, and that is important, if the first coefficient is not 1, if it's anything other than 1, what I'm about to show you doesn't work. But this is a shortcut or a method for factoring a trinomial if the first coefficient here is 1, if there's no other number here before x squared. Like this one here, there's no number here. It's like 1x squared, 1x squared. So this method will work for all 3 of these. when we're looking at our original problem, x plus 3 and x plus 4, if we add these numbers together, 3 and 4, we get 7. And if we multiply these numbers together, 3 times 4, we get 12. That's a really useful pattern to see, because if we want to work this backwards, the questions we need to ask are, what are two numbers that multiply to 12 that also add to 7? Well, if you go through your factors of 12, 2 times 6 is 12, but 2 plus 6 is not 7. 1 times 12 is 12, 1 plus 12 is not 7. 3 times 4 is 12, and sure enough, 3 plus 4 is 7. Let's look at this example here, this next one. Again, no coefficient, no leading coefficient, we would say, except for a 1 here, 1x squared. So we can ask, what are two numbers that multiply to 5 that also add to 6? Well, the only whole numbers that multiply to 5 are 1 and 5. And sure enough, 1 plus 5 is 6. So this would factor to x plus 5 times x plus 1. And if you took a minute, paused it, and distributed this through, if you FOILed it out, x times x would be x squared, 5 times x would be 5x, x times 1 would be 1x, 5x and 1x would give you the 6x, and 5 times 1 is 5. So it does work. Again, in the last example here, first leading coefficient is 1, so we can use our shortcut, our method. Two numbers that multiply to 18 that also add to 9. Well, 9 times 2 is 18. 9 plus 2 is not 9. 6 times 3 is 18. And yep, 6 plus 3 is 9. So we're looking for two numbers that multiply to the trailing coefficient here, the last coefficient, that also add to this middle coefficient here. And 6 times 3, or 6 and 3, would work. Once you have those two, I will point out, because of the commutative property, it doesn't matter if you do x plus 3 first and x plus 6 second, or x plus 6 and x plus 3. That doesn't matter. As long as you have the 6 and the 3 and the x plus and the x plus, you're good to go. So it doesn't matter the 3 and the 6, which one comes first, as long as you have those two important numbers. Okay, I've got 4 examples. I do want you to actually pause it. I want you to try these 4 problems. Write them down. It's very different doing it on your own than watching me do it. Listening to me go through the problems and doing it on your own is a very different thing. So please do pause it. Try these 4. I'm going to show the answers. I'm not going to show how to do all 4. I want to make sure the videos keep moving. I'm going to do a follow-up video, so there'll be a second link where I show how to do those 4 problems. That also means if you get these 4 problems right, don't worry about watching the explanation, move right along. If you get any of these wrong, please watch the extra couple minutes in the second video and see how to do them correctly. So if you get these 4 right, awesome, move on. If you get any of these 4 wrong, please take a moment to watch the second video and look at how to do them. So okay, go ahead, pause it, try it on your own. I'm assuming you paused it. I'm assuming you tried it on your own. I'm going to reveal the answers. If those are the answers you got, great, move on, you've got it. If you got anything other than these 4 answers, please move, or you can watch the rest of the video if you want, but then go into the second video that's linked in the XYZ homework section here and watch how to do those 4 problems. Again, the only thing that you wouldn't have to watch the video for is if you had x plus 4 and x plus 10. As long as you have those 2 numbers, this does need to be a minus 3 and a plus 9, a plus 2 and a plus 8, then you're good to go. So if you have these flip-flopped with the commutative property, that's okay. As long as you have those numbers, the plus and the minus are important. So make sure you have the subtraction and the addition in the right spot. All right, moving on. Difference of perfect squares. I mentioned that these were going to be very useful when we, as we move forward in this chapter as well as subsequent chapters. So if we had 4x plus 2 and 4x minus 2, they were conjugates, then the shortcut was we get 16x squared minus 4. We multiply the first terms together. 4x times 4x is 16x squared. 2 times minus 2 is negative 4, and that, or minus 4, and those middle terms canceled to 0. They added to 0. If we had 5x plus 6 times 5x or times 5x minus 6, you do the same thing. 5x times 5x is 25x squared. 6 times 6 is negative 36 or minus 36. So that was that difference of perfect squares. What I want you to try and do then is rewrite these as their conjugates. So go backwards through this process. 25x squared minus 36, write that as two different factors. 16x squared minus 4, write that as two different factors. So again, pause it. Try and rewrite these as their two factors, the two binomials being multiplied together. If you get them right after I show the results, great, move on. If you get any of these wrong, or if you have no idea where to start, you're not even sure what I'm asking you to do, then watch the follow-up video. So there'll be a linked video after this that I'll encourage you, or I'll ask you to watch how to do them step by step. So pause it, try it on your own. Assuming you paused, and I'm assuming you tried it on your own, here are the answers, here are the results. Again, it doesn't matter if you have the x minus 12 first and the x plus 12 second, as long as you have a plus 12 and a minus 12, as long as you have a plus 1 and minus 1. As long as you have these two different binomials being multiplied together, you're correct. If you didn't get those right, or if you, especially maybe that last one, look at the linked video. You can pause, fast forward to the one you need, whatever, but look at that last video on how to do these three questions. Moving on, last little bit here. Factoring again, but more. If the leading coefficient isn't a 1, it's a little more complicated. In fact, it's a lot more complicated. And there are two methods that I'm going to show for this, and I'll let you decide which one you want to do. So you've got 3x plus 1 times 2x plus 5. And if you distribute that through, 3x times 2x, 3x times 5, 1 times 2x, and 1 plus 5, and you combine your like terms, this is the result that you're going to get. What we're going to be asked to do then is to work that backwards. And this is where I'm going to move over to the document camera, and we're going to look at two different ways to do this. One way is what's called the AC method. You may have seen this in previous classes. If you haven't, I'm going to show it. If you don't like it, don't use it. I'm going to show you a second method. I don't have a third, so you really either need to make up your own or pick one of the two that I have or look one up online. But these are two of the more common methods. So the AC method, the way this works is you multiply the first term and the last term together. So 6 times 5. And there's no math behind this. Like, there's no reason we can do this. It's just a method that we're going to use. So 6 times 5 is 30. And then we're going to look at this middle term here of 17. Okay, now again, the 6 times 5, there's no mathematics going on here. It's just kind of a trick. It's a method. It's a way to do it. And we're going to ask a similar question to what we asked before. After you multiply the first and the second term, or the first and the last term, together, we're going to ask what are two numbers that multiply to 30 that also add to 17. So multiply to 30, I know 6 times 5 is 30, but 6 plus 5 is not 17, so that doesn't work. 2 times 15. 2 times 15, that's 30. And 2 plus 15, that's 17. Once you have those two terms, the 2 and the 15, we're going to rewrite this original problem. We're going to keep the first term the same, 6x squared, but 17x, we're going to rewrite that as 2x plus 15x. So that's 17. We broke it up as 2 plus 15. It's 2x plus 15x. So we're just breaking this up. We're just breaking up in a very special way, though. And the plus 5 at the end, we're going to keep there. Now what we're going to do is what's called factoring by grouping. And this is going to come up later on, too. But factoring by grouping is what we're looking at next. We're going to look at the first half of this term. Whoa, you can't see that when I do it. Let's try that again. So we're going to look at the first half, 6x plus 2x. And we're going to say, what can I factor out of both 6x and 2x? Well, I can factor out a 2, can divide both 6 and 2 by 2, and I can factor out an x. They both have an x that I can pull out of it. So I'm left with, then, 3x plus 1. I divided out a 2x from both of those terms, left with this. Now I'm going to do the same thing for the second half. 5x plus, or excuse me, 15x plus 5. I'm going to ask, what can I factor out of both of these? Well, I can divide a 5 out of both of them. The greatest common factor between 15 and 5 is 5. And I'm left with 3x plus 1. Now, if you're doing it correctly, it should work out that these two in the parentheses here are the same, 3x plus 1 and 3x plus 1. And this is where it gets a little more complicated, and more so than we've already made it. And I'll tell you kind of the thought process. I'll also tell you the really specific mathematical end of it. What we're looking at now is what can we factor out of both of these terms? And we can factor a 3x plus 1 out of both of these terms. What we're left with is a 2x plus 5. Now that's the mathematical way of thinking about it. What can we factor out of both of these terms, a 3x plus 1? The other way to think about it, or to look at it anyways, is it appears that we're just putting these together and we're grouping what we have outside the parentheses together. And that's effectively what you're doing. We're not going into the mathematics. That's the answer. And that's called the AC method. The other method that I'm going to show is, so that's AC method. That's the solution we get. The other method is to ignore the middle term, ignore the 17, and just look at the first term and the last term. And we're going to ask, what are two numbers that multiply to 6, and what are two numbers that multiply to 5? Well, two numbers that multiply to 6 are going to be 3 and 2, I guess. And the two numbers that multiply to 5 would just be 1 and 5. 1 times 5 is 5. And now we're going to do what's called the rainbow. Taste the rainbow. We're going to do 2 times 1 and 3 times 5. So we're going to multiply the inner two terms and the outer two terms. 3 times 5 is 15, and 2 times 1 is 2. If I have the right terms, and they're in the right order, they should add to 17. Should match with that middle term there. And it does. Now I'm going to write my solution. The 3 comes straight down. We get 3x. The middle two terms are going to crisscross. And I'm going to get 3x plus 1 and 2x. And then the last term comes straight down. 2x plus 5. You'll notice it's the exact same solution, once I get my hand out of the way, it's the exact same solution as our AC method. You decide which one you like better. If you're looking at this and going, I don't get that, don't use it. Use the AC method. If you have seen this method before and you prefer that one, use this method. It's completely up to you. And I'll show them both again in a different problem. Okay. I think I'm getting long in the video here. So I'm going to ask you to try these two. Rather than extending this video even more, I'm going to do a third follow-up video. So if you don't understand that, the AC method or the other one, you need to see some more examples. Watch the linked video on that. But I'm gonna give you a chance. Pause it. Try these on your own. I'm assuming you paused it. I'm assuming you tried it on your own. Again, trying it on your own is way different than watching me do it. But here are the solutions for these two problems. If you didn't get those, or if you're completely lost by the end of it there, go back, watch those linked videos, and make sure that you do some more examples and see how these are done. Okay, that is the end of this section.